Hi students, in this video we are going to discuss our third colligative property and which is called a depression of freezing point. So we'll be lowering the freezing point. Depression just a fancy word for a lowering. Now what we are going to see here, we'll be mixing some non-volatile solute again. We'll make a solution and if we'll try to freeze it, now we will see that the freezing is happening at the lower temperature. Now why that is happening? So here I have taken water and I have put that in fridge. So these are the water molecules and please remember they are not stationary like that. Nothing is stationary in this world. So they are buzzing around. That's why they are liquid. They can move around. Okay. They can pass, they can move past each other. So the real picture is not like that. It's kind of an animation. Imagine that. Every molecule is free to go, right? They are vibrating. So they have enough kinetic energy. They have enough kinetic energy. Now what will happen that when we are freezing that, we take heat out, right? We take heat out. So this guy was very happy, okay, at this room temperature. But now when it comes to fridge, it slows down, right? It slows down. And when it is slowing down, the bonds between these two molecules, they take over. They are able to bind them. So in waters, what kind of bonding we have? We have hydrogen bonding, intermolecular forces. So what will happen? These molecules, when they are slowing down, because you are taking heat out, they are having less kinetic energy now. What will happen? A time will come when they will establish a solid bond, we can say, between each other. They will try to remain at one place around. It is not completely stationary, remember that. So that they have started solidifying. They have started to make, lattice, a solid structure. So what happens at 0 degree centigrade? This is called a fancy name, freezing point. So at that point, they have lowered, we have taken so much heat so that they are able to establish the solid lattice between them. So these intermolecular forces have are enough to put them at one place, right? The kinetic energy is still there, but these intermolecular forces are able to create structures, right? Lattice they are able to make, and that's why you see the solid ice. So this is what is called, solidifying, or what is happening in the normal scenario when the pure solvent is there. So now here comes the villain, our salt, say. So I mix salt with it, salt with water now. Non-volatile, remember. So I will place this molecule, let's say, is a salt particle. Now what will happen? Same thing, we have put that water in the fridge, but now the salt is mixed. Now what will happen? We have to lower the temperature, we are taking heat out, and these molecules which were buzzing around, in the at the room temperature, now because heat is taking out, they will go slow, 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 and they are reducing their kinetic energy, right? And at 0 degree centigrade, what will happen? They should be able to create a bond between these two molecules, but now what? Here is a villain in between, right? He will be able to hinder it. He will able to restrict them. He will able to resist them to create these bonds because of their presence. They are coming in between. And that is why it is not easy for them at this kinetic energy. Let's say they have this kind of speed. At that time, without solute, they were able to create bond, but now they are not. They need more energy to be lowered, and that is why you have to lower this energy, let's say 2 degrees centigrade, minus 2 degrees centigrade, and now we have taken more heat out, right? We have to take more heat out because we want to negate the effect of the solute particle, and with such a less energy, now they are able to create, bonds and create structures, lattice structures, and then they will be able to freeze. So here the intuition we can build on. So let's say there are two molecules at room temperature of water, which you have, kept at room temperature. So why they are not freezing? Because they have much kinetic energy, right? Both are buzzing around. Yes, there are hydrogen bond between, but they are not able to keep them at one place. They are not able to keep them in the lattice. So now when you put that in the fridge, in the pure solvent, it, the kinetic energy becomes lesser, 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 and now these bonds, they can win, right? They can able to hold them at one place and able to create structure. So that is happening at normal 0 degree centigrade, right? And now what will happen? When we are mixing the solute particle, they are coming in the way, you can say, right? So even at this kinetic energy, at 0 degree centigrade, they were able to do. But now with the presence of this guy, because they may come in between, they can get in the way of forming the bonds. They need more energy to be lowered so that this hydrogen bonding can win. So that's why we need to take out more energy, minus 2 degrees centigrade. Let's say we have lowered the freezing point, so the kinetic energy becomes more or less. And now they will say, even if this guy is there, hydrogen bonding will say, even if this guy is there, their kinetic energy is so less, I'll be able to hold them. I'll be able to make the lattice structure. So we understood the presence of solute particle, how it is making harder to hydrogen for hydrogen bonds to be formed as a solid lattice. But lowering the vapor pressure also makes a mark. See, if for the water, if it wants to release its energy, let's say this molecule have lot of kinetic energy, right? So it can go into the vapor state, higher energy state. But now, because we have solute particles on the surface, right? And these water molecules are binded with them, right? Colligative, binded. So they are having higher kinetic energy, they cannot escape. So they have more energy, we can say, in a way. So they are keeping more energy here, right? So how at this energy, this much energy, they will be able to create the bonds, hydrogen bonds. The hydrogen bond will say, no, it's such energy, I cannot form the bonds. So that is why we need to take more heat out. So we can say at 0 degree centigrade, हमारा काम नहीं चलेगा. 0 degree centigrade, this energy is not enough. So we have to lower, right? Lower the freezing point. So the water will get in control. You can say this water molecule will get control with the hydrogen bonding only at the lower temperature, so that we will see that the solution is freezing at the lower temperature. And this phenomena is what we are calling depression of freezing point. Now let's do the numerical part of it. As it is a colligative property, it will be depending on the number of solute particles. Somehow that has to be introduced. So the depression delta T, okay, change in temperature, and we are telling about the freezing depression, that will be equal to Kf. So remember that this is the similar formula as we were doing elevation in boiling point, and the similar things will come. Okay, so this is what M is. Remember, this is not X, this is M, which is called molality. And in the last video, we have discussed how to, keep it in a simple formula. What will be this called? This will be called molal. In elevation of boiling point, it was called molal elevation constant. This is depression, so it will be called molal depression constant. This value is a constant found by experiment. So using this formula, we'll be able to calculate how much, we have to lower the temperature to get the freezing point. How much the change in the freezing point we can have if we have such a configuration. Thank you.